Something is happening in the corner of the room. There is a version of the universe where everything you haven't looked at yet is still real, where the cup on the counter, the key in your coat pocket, the moon on the far side of its orbit, all of it continues existing completely, whether or not you turn to check. You have always assumed this. You assumed it before you had language for it. You assumed it the way you assume the floor is there before your foot lands. Einstein assumed it too. He built his life's work on it. And then, in 1935, he co-authored a paper designed to prove quantum mechanics was incomplete, and instead, without meaning to, he pulled a thread that would spend the next 90 years unraveling something most physicists hadn't even noticed was stitched together. The thing he pulled on wasn't an equation. It was a feeling. The feeling that reality doesn't wait for you to look at it. There's a specific kind of discomfort that comes when something you never questioned turns out to have been a choice, not a mistake. A choice. You picked a version of the world and called it obvious, and it mostly worked, and then one morning someone shows you the part where it doesn't, and you can't find the place to put that information. If you've ever felt that, in any context at all, you already understand what this paper did to 20th century physics. Leave a comment if you know what that feeling is like. I suspect more people have a version of it than usually say so. Here is the fact that started everything, and it will probably sound too simple to matter. Quantum mechanics says that certain properties of particles don't have definite values until they are measured. Not that we don't know the values, that the values aren't there to be known. The particle is not hiding its spin the way a coin hides its face while it's in the air. The coin analogy doesn't work. The particle genuinely does not have a spin until the spin is observed, at which point it has one, and the universe updates accordingly, and everything downstream of that update has to catch up. Einstein found this offensive. That is not an exaggeration or a softening. He found it philosophically offensive in the way you find it offensive when someone rearranges your home without telling you and insists the new arrangement was always correct. He had spent decades building a physics where causes preceded effects, where nothing travelled faster than light, where the universe could be described completely by quantities that existed independently of whether anyone was checking. He called this realism. It seemed obvious to him. It seems obvious to most people. It is the kind of obvious that lives below the level of questions, the way breathing is obvious, the way you don't usually notice you're doing it. The discomfort starts when you realize that quantum mechanics is not describing a different universe. It is describing this one. And for a long time, decades really, the dominant response in physics was a kind of sophisticated looking away. Quantum mechanics worked. It produced predictions that matched experiments to a precision that made other theories look like guesses. So physicists used it. They used it the way you use a tool whose mechanism you haven't fully thought about, because the tool works and the job is in front of you, and there will be time to think about the mechanism later. There was not, as it turned out, a good reason to wait. But before the experiments, before Bell, before the slow, systematic dismantling of the alternative, there was just the feeling Einstein had, the feeling of standing in a room that seems completely normal and noticing, just for a moment, something in the corner that shouldn't be there. Not dangerous, not impossible to ignore, just wrong, in a way that doesn't announce itself. That is where this chapter lives, in the moment before anything is resolved. The EPR paper, Einstein, Podolsky, Rosen, 1935, asked a very specific question dressed up as an argument. It said, if quantum mechanics is correct, and if two particles can interact in such a way that their properties become linked, then measuring one particle should instantly tell you something about the other, no matter how far apart they are. This was not presented as wonder, it was presented as a problem. Because if measuring particle A instantly determines something about particle B across any distance, then either information is travelling faster than light, which Einstein's own relativity forbids, or quantum mechanics is not telling the whole story. There must be something underneath, some variable the theory hasn't found yet, something that was always there, determining the outcome before anyone looked. This is called the completeness question, and the word completeness is doing a lot of quiet work in that sentence. A complete theory, in the sense Einstein meant, would describe every element of physical reality, not just what we can measure, everything. If the particle has a spin before you measure it, a complete theory would say so. If the particle doesn't have a spin until you measure it, a complete theory would have to explain why the universe works that way, not just note that it does. Quantum mechanics, in Einstein's reading, was doing the second thing and calling it done. He wanted the first thing. He thought the first thing was the only kind of physics that deserved the name. What makes this hard to sit with is that he wasn't obviously wrong. He was asking a question that sounded like the right question to ask. He was asking whether the theory was finished. The answer, it turned out, was complicated. Not yes, not no. Something more like, the question itself needs to be taken apart before it can be answered, and once you take it apart, you find that one of its pieces was built on an assumption so old that nobody remembered deciding to make it. That assumption had a name. It still does. It is called locality. Locality says that what happens here cannot instantly affect what happens there. That objects are influenced by their immediate surroundings. That the universe is not one continuous thing in which everything is always touching everything else, but rather a place made of separate parts that interact through contact, through signals, through chains of cause and effect that take time to travel. It sounds like physics. It is also just how rooms feel. When the light goes off in the kitchen, the lamp in this room doesn't notice. Things here are not things there. Causes travel. Effects wait. This is so embedded in how we experience anything that pointing it out feels almost rude, the way it feels rude to explain a joke. Quantum mechanics, in certain configurations, does not behave this way. Not dramatically. Not in a way that allows for faster-than-light communication, or that would let you send a message backward in time, or that would cause the kitchen lamp to notice anything. The effect is subtler and stranger than that. It lives in the statistics. It lives in the patterns that emerge when you run the same experiment thousands of times and notice that the correlations between distant particles are too strong in a specific mathematical sense to be explained by anything that was determined in advance. But in 1935, that measurement hadn't happened yet. That measurement was 30 years away. What existed was only the argument. If quantum mechanics is right, then the world must be the kind of place where things that are nowhere near each other are still, in some sense, touching. And Einstein did not believe the world was that kind of place. He was wrong, as it turned out. But the wrongness is not the interesting part. The interesting part is the thing underneath the wrongness. The assumption he was protecting, the floor he needed to be solid, the room he had spent his entire scientific life furnishing, and how much the field of physics owed to the fact that he refused to let it go. Something about the corner of a room, late at night, with everything quiet. There is a moment in certain kinds of understanding where you have been told something true, and your mind has registered it as information, but your body hasn't processed it yet. The sentence has landed. The meaning is still travelling. You know the fact, but you haven't felt it settle. That is the state this chapter is trying to put you in. Not full understanding, not confusion. Something between them, where the ground is still there but feels slightly less certain than it did a few minutes ago, and you're not sure yet whether that is because something is wrong or because something is, finally, more accurately right. The paper Einstein wrote with Podolsky and Rosen was 9 pages long. It was published in the Physical Review on May 15th, 1935. It was designed to close a door. It opened one instead, and the door is still open. And what is on the other side of it is not nothing. The man who needed the floor to hold. There is a particular kind of mind that does not experience uncertainty as a temporary condition. Most people move through not knowing the way they move through weather. It is unpleasant, it resolves, they continue. But there is another kind, rarer, where uncertainty is not an inconvenience but a structural problem, where the absence of a solid foundation doesn't produce mild discomfort, but something closer to a permanent low hum of alarm, and where the entire project of a life can be understood as the attempt to build a floor solid enough that the hum finally stops. Einstein was this kind of mind. Not in the way that made him difficult, or not only in that way. In the way that made him precise. In the way that made him unwilling to accept an answer that worked statistically if it didn't also work philosophically. Unwilling to call something understood if the understanding was purely operational, if you could use it but couldn't say what it was describing. He wanted physics to describe something real. This seems like a reasonable thing to want. It seems actually like the obvious thing physics is for. But the history of the 20th century is partly the history of physics discovering that what is real and what is describable are not always the same territory. And Einstein was, more than almost anyone, the person who could not make peace with that gap. He was born in Ulm in 1879. This is a fact that settles slowly, the way most biographical facts do, by giving you a context without yet explaining why it matters. What matters is not the year, but the shape of the intellectual world he was born into. Classical mechanics, Newtonian gravity, Maxwell's electromagnetism, a physics where the universe was a vast and orderly mechanism running forward through time according to rules that could be written down and trusted. Causes produced effects, objects had positions, fields carried forces. The universe, if you knew everything about it at a given moment, was in principle predictable, completely, forward and backward, forever. This was not just a scientific position. It was the ambient texture of what educated people believed the universe to be. He grew up inside this. He absorbed it before he had the tools to question it. And then, in his early 20s, he began questioning everything else while leaving this particular thing. The fundamentally orderly, locally causal, realistically described universe, largely alone. His special relativity in 1905 overturned Newtonian mechanics and rewrote time and space, but it did so in a way that preserved locality, preserved causality, preserved the sense that the universe was made of things that existed whether or not anyone was looking at them. His general relativity in 1915 curved space-time itself, introduced a gravity that was geometry rather than force, described the large-scale structure of the cosmos with a precision that still holds a century later, and again, throughout, the universe in his equations was a real place, fully described, operating according to rules that were not statistical but exact. He had made the universe strange in ways nobody had managed before, but it was still a universe where the flaw held. What quantum mechanics offered, in the years when it crystallized into its modern form, roughly 1925 to 1927, through the work of Heisenberg and Schrödinger and Born and Bohr and a handful of others who were, most of them, much younger than Einstein, was a different flaw entirely. Not a flaw that had been dug up and replaced with something more accurate. A flaw that wasn't there, or rather, a framework that said the question of what the flaw is made of when no one is in the room is not a question physics needs to answer. The Copenhagen interpretation, which became the standard reading of quantum mechanics and remained so for decades, said essentially this: quantum mechanics describes the outcomes of measurements. It gives you the probabilities of what you will find when you look. It does not tell you what was there before you looked, because that question may not have a meaningful answer. The particle's position, before you measure it, is not hidden from you. It is genuinely undefined. It exists in a superposition of all the positions it could have, weighted by probabilities, and it arrives at a definite position only at the moment of measurement, which is called collapse. And what exactly does the collapsing is a question the Copenhagen interpretation prefers not to sit with for too long. Einstein read this and felt something he almost never felt, that he was being asked to accept something on grounds he found insufficient. He was not, it must be said, a religious man in any conventional sense, though he used the word God frequently, usually to mean something like the underlying order of things, the deep consistency of the universe that he took on something close to faith. When he said that God does not play dice, which he said in a letter to Born in 1926 and variations of which he repeated for the rest of his life, he was not making a theological claim. He was making a claim about what a complete physical theory must look like. He was saying that a theory whose fundamental outputs are probabilities, whose best answer to what will happen is always, here is the distribution of possibilities, is a theory that is describing something in front of the actual answer, not the actual answer itself. He was saying, there is something underneath. There has to be. Born wrote back gently and told him that many people found the theory satisfying. Einstein replied also gently that this was not the point. The exchange is worth pausing on, not for what it says, but for what it reveals about two different ideas of what physics is supposed to do. Born thought physics was supposed to predict correctly. Einstein thought physics was supposed to describe truly. Both of these seem reasonable. They are not always the same project. For most of the history of science, they had been the same project closely enough that no one needed to distinguish them. Quantum mechanics was the first major case where predicting correctly and describing truly appeared to come apart. where a theory could be spectacularly right about everything you could measure while being, in Einstein's view, silent about everything that actually mattered. He spent the decade between 1925 and 1935 trying to find the crack. He proposed thought experiments at the Solvay conferences, each one designed to show that quantum mechanics led to a contradiction, each one answered by Bohr with what Einstein privately found insufficient but could not formally refute. He lost the debates by the consensus of the people watching. He never felt he had lost the argument. He felt instead that Bohr was very good at explaining why the paradox wasn't there without actually making the paradox go away. Then came 1935, and the paper and the specific form of the argument he finally found he could make cleanly. He worked on it with Boris Podolsky and Nathan Rosen, two younger physicists who were at the Institute for Advanced Study in Princeton with him. The argument did not require any new physics. It required only that you follow quantum mechanics to one of its conclusions and notice what that conclusion implied. The conclusion was this: if you allow two particles to interact so that their quantum states become correlated, what the theory calls entangled, though Einstein did not use that word came from Schrödinger, who read the paper and coined the term within months. And then you separate those particles and measure one of them, the quantum state of the other particle updates instantly, instantaneously, not quickly, not with a small delay proportional to distance, instantly. The moment you find that particle A has spin up, particle B is spin down, no matter where B is, no matter how far. This, Einstein said, was impossible. Not impossible because quantum mechanics had made a mathematical error. Impossible because one of two things had to be true, and both of them were deeply problematic. Either the measurement of particle A was somehow sending a signal to particle B faster than light, violating special relativity, or particle B had always been going to be spin down, and the answer was encoded in the particle all along, and quantum mechanics simply hadn't been keeping track of it. The first option he found unthinkable. The second option meant quantum mechanics was incomplete. He preferred the second option. He believed, with the settled conviction of someone who has thought carefully about something for a very long time, that there was information the theory wasn't capturing. He called it the hidden variable. He didn't know what it was. He was confident it was there. The paper was published. Bohr responded. The response, as responses go, was philosophically committed, and to many readers not quite responsive to the actual argument. The community mostly moved on. The questions it raised were considered either solved or unanswerable or both, which amounts to the same thing in practice, which is that people stop asking them. But the paper left something in the room, a residue, a question shaped like a certainty. If those particles, separated by any distance, are still coordinated in their outcomes, if measuring one tells you instantly what you would find in the other, then either something is travelling between them or they were never really separate. Einstein believed they were separate. He believed this the way he believed in the flaw. He believed it the way a person believes in the things that have to be true for everything else to make sense. The flaw did not go anywhere while he was alive. He died in Princeton in 1955, still working, still unsatisfied, the hidden variable still hidden. What happened next? The theorem, the experiments, the slow, careful dismantling of the alternative. He did not live to see. But the question he asked was the right question. even if the answer was not the one he needed. 2 coins, 1 flip. Start here, 2 particles, same source, same moment of origin. They separate, one goes left, one goes right. The distance between them grows, a meter, a kilometer, the width of a city, the distance between continents, further if you want. The numbers don't change anything that matters. They are moving away from each other at whatever speed you arrange. They are, by any ordinary measure, no longer connected. Except they are, not by a wire, not by a signal travelling between them, not by anything you could point to or intercept or block. The connection is not in the space between them. The connection is in what happens when you look. You measure the left particle. You find it has a property, call it spin, because that is the actual term, though the word spin here does not mean what spin means for a top. It means something like a quantity that can only be found in one of 2 states, up or down, when you go looking for it. You find it is up, and at that moment, in that instant, if someone measures the right particle, they find it is down. Always, every time, without variation. The correlation is perfect. This sounds like it could have a simple explanation. The simple explanation is this: the particles were always going to do that. They left their common source with a predetermined arrangement, one encoded to be up, one encoded to be down, and when you measured them, you simply discovered what was already there, like reaching into a bag of gloves and finding a left glove in your hand. Of course, the one remaining in the bag is a right glove. This is not mysterious. This is just inventory. That explanation is wrong. It is not wrong because it sounds too simple. Simple explanations are often correct. It is wrong because of what the particles actually do when you change the question you are asking. Here is the thing about spin. You can measure it along different axes. You can ask, what is the spin along this direction? Or along that direction? Or along this other direction 45 degrees from the first? These are different questions. They produce different answers. And quantum mechanics makes a specific, testable prediction about how the answers correlate across particles when you measure them along different axes. The prediction involves a number. The number comes from a calculation. The calculation produces a limit. That limit is what matters. If the particles were like gloves, if they had always carried their answers inside them, predetermined, waiting to be discovered, then the correlations between their measurements across different axes, across many repeated experiments, would have to stay within a certain range. The math is not obvious, but the conclusion is there is a ceiling on how correlated 2 separate locally predetermined things can be. The ceiling is a number. Bell calculated it in 1964. The ceiling is now called a Bell inequality. Quantum mechanics predicts correlations that go above the ceiling. Sit with that for a moment. Not the math, the shape of it. There is a limit on how much 2 separate things can agree with each other if their agreement was set up in advance. Quantum mechanics says particles agree more than that limit allows, more than any locally predetermined arrangement could produce. If the experiments confirm the quantum prediction, and they do, which is a later chapter, then the particles are not like gloves. They were not carrying predetermined answers. Something else is happening. What is happening has a name. The name is entanglement. An entanglement is not a signal. This is the part that creates the most confusion, because the word connection suggests communication, and communication suggests information travelling, and information travelling suggests speed, and speed suggests limits, and the limit is light, and light takes time. But entanglement doesn't travel. There is nothing moving between the particles when you measure one and the other one updates. The correlation exists. The correlation is not transmitted. It is just there, in the relationship. The way two ends of a single object move together not because one end sends a message to the other, but because they are one object. Together not because one end sends a message to the other, but because they are one object. Except they are not one object. They are in different places. They separated. That is the part that doesn't resolve cleanly, the part that Einstein found untenable, the part that still sits in the middle of the table, without anyone being quite willing to say they understand it fully. What you can say is this: the particles share a quantum state, not one particle each, but a single quantum state that belongs to both of them together, and that state does not decompose neatly into a state for particle A and a state for particle B. The pair is the unit. The pair is what has the definite quantum description, and neither particle alone does. When you measure one particle, you're not discovering something about it in isolation. You're performing an operation on the pair, from one location, and the other end of the pair, wherever it is, reflects that operation immediately. This is what the EPR paper was pointing at, not with wonder, with alarm. Because if this is true, if the pair is the unit, if measurement at one location affects the state description at another location instantaneously, then locality is not intact, not in the way Einstein needed it to be. Something about the universe is not separable into independent local parts the way he had always assumed. The parts are parts of something, and what they are parts of does not live in any particular location. There is a word for this too. The word is non-locality. Einstein called it spooky action at a distance, in German, which he did not mean as a compliment, and the phrase has lasted because it is more honest than most technical vocabulary about what the thing actually feels like. It feels like something that should not be possible is quietly being true in every corner of the universe, all the time, in every pair of particles that has ever interacted and separated, which is an incomprehensible number of pairs, which means the universe is laced with these invisible correlations, these non-travelling connections, these relationships that span any distance without sending anything across the distance, and none of it violates any law you can measure, and all of it has been there the entire time, running quietly under everything, while we arranged our lives according to the assumption that separated things are separate. The two coins flip. They always land opposite. You never catch anything moving between them. And yet the result is never random between them. And this has been true for every entangled pair since the beginning of the universe, and the beginning of the universe produced quite a lot of them. What he actually said. The paper was 9 pages. When it was done, Einstein felt it had not quite said what he meant. This was not unusual for him. He often felt after a thing was published that the argument had gone slightly sideways in the writing, that the version on the page was not quite the version in his head, that something clean had become slightly approximate in the translation from thought to sentence. Podolsky had drafted most of it. Einstein had not been pleased with Podolsky's draft. He had been more not pleased after the paper appeared, and the response it generated suggested that people were reading it as a more frontal attack on quantum mechanics than he had intended. What he had intended was narrower, and in some ways more devastating. The paper was called "Can Quantum Mechanical Description of Physical Reality Be Considered Complete?" The title is doing significant work. It is not asking whether quantum mechanics is wrong. It is asking whether it is finished. These are different questions, and the difference between them is the thing the paper is really about. The thing Einstein spent the rest of his life circling, returning to from different angles, arriving at the same place each time. A complete description of physical reality, the paper argued, must include every element of that reality. This sounds tautological. It is meant to. The point is to establish a criterion so obvious that refusing it requires admitting something uncomfortable. The criterion is called the reality criterion, and it says, if you can predict the value of a physical quantity with certainty, without disturbing the system in any way, then there exists an element of physical reality corresponding to that quantity. The thing you can predict exists. Whatever lets you predict it must be real. This is not a strange claim. This is just what it means to say that physics is about something. Now the argument. Two particles, entangled, separated. You measure particle A and find its spin along a particular axis. Because of the entanglement, you now know with certainty what you would find if you measured particle B along the same axis. You know this without touching particle B. You know this without disturbing it in any way. So by the reality criterion, the spin of particle B along that axis is an element of physical reality. It exists. It has a value. It was there before you looked. But quantum mechanics says no particle has a definite spin before measurement. The value comes into existence at the moment of measurement and not before. If the spin of particle B existed before you measured it, then quantum mechanics was failing to account for something that was actually there. If it didn't exist until you measured particle A, then measuring particle A somehow reached across whatever distance and affected particle B, which violates locality, which Einstein found worse than the first option. So either quantum mechanics is incomplete, or locality is false. He chose incomplete. The argument has a name now, the EPR argument, or sometimes the EPR paradox, though Einstein did not think it was a paradox. He thought it was a proof. He thought he had demonstrated, cleanly and without drama, that there was more to the universe than quantum mechanics was tracking. He had demonstrated something. What exactly he had demonstrated would not become clear for 30 years. Bohr read the paper within weeks. Bohr's response appeared in the same journal later that year, under the same title with a different inflection. It was careful. It was long. It agreed with the math entirely. It disagreed with the conclusion by disagreeing with the premise, specifically with the reality criterion, specifically with the idea that you can speak meaningfully about a physical quantity when the measurement has not been performed. Bohr's position compressed. You cannot separate the particle from the measurement apparatus. The question of what spin particle B has, in the absence of any measurement of particle B, is not a well-formed question. There is no fact of the matter. The reality criterion assumes there is a fact of the matter independent of measurement, and that assumption is exactly what quantum mechanics is telling us to give up. Einstein read this and was not satisfied. He had expected to not be satisfied. He thought Bohr was very good at refusing the question rather than answering it. The argument went circular. It has remained circular ever since, in a sense. What Bohr called a resolution, Einstein called a refusal. What Einstein called a proof of incompleteness, Bohr called a misunderstanding of what completeness means. Both were right about something. Neither was right about everything. The argument needed a third thing, a test. Something that would make the two positions produce different numbers and let the universe choose. That thing didn't exist yet. It would take another 29 years. Until then, the paper sat, cited, read, argued over at conferences, quietly filed under foundational questions that don't affect the calculations. The field moved forward. Quantum mechanics continued producing correct predictions. The question of whether those predictions described something real or just described the statistics of measurement was considered, by most working physicists, a philosophy problem. Philosophy problems do not go away. They wait. Bohr in a room, alone. You would think, if someone built the most successful scientific theory in the history of measurement and then spent the rest of their career defending it from a man who was arguably the greatest physicist alive, that the defense would feel triumphant, victorious maybe, at least settled. You would think the person doing the defending would sleep easily, which is not a small thing, and would move through the remaining years with the particular lightness of someone who knows they are right. Niels Bohr did not seem to feel that way. He was not a man who doubted the theory. He had helped build it and believed in it with the kind of deep, structural confidence that comes from having understood something from the inside, from having seen how all the pieces fit, from having watched it produce correct answer after correct answer in situation after situation. But he was also a man who thought carefully about what the theory was saying, not just about what it was predicting, and what it was saying was strange enough that careful thought about it produced a face that often looked, to the people around him, like a man working through something he had not finished working through. He once said, in a version of a remark he made several times in several forms, that if you're not shocked by quantum mechanics, you have not understood it. He was not performing humility. He was reporting a condition. The condition was this. Quantum mechanics seemed to be saying that the properties of things do not exist independently of the act of measuring them, that there is no fact about a particle's spin or position or momentum until a measurement apparatus interacts with it, and that the wave function, the mathematical object that encodes everything the theory knows about the particle, is not a description of what the particle is doing, but rather a description of what we would find if we looked. And these two things are not the same thing, and the difference between them is not a minor technical distinction, but an absolute chasm in what we mean when we say that physics describes reality. Bohr's response to this chasm was to say, the chasm is correct, not to close it, not to find a bridge, to say, yes, that is the shape of things, and the fact that it does not match our intuitions derived from the behavior of large objects at human scales is not a problem with the theory. It is a problem with our intuitions. This is either very wise or a form of looking away, and I am genuinely not certain which, even now having spent a long time thinking about it. The argument he made against Einstein in the EPR response was essentially a philosophical one. You cannot define the properties of a system independently of the experimental context in which those properties will be measured. The particle does not have a spin out there waiting to be found. It has a spin relative to a measurement, and the word relative is doing everything in that sentence. It is carrying the entire weight of the disagreement. Because Einstein's relativity also involved things being relative to reference frames, and he had made peace with that decades ago. But this was a different kind of relative. Relative not to motion or velocity, but to the act of observation itself. Relative to whether anyone was looking, and this was the version of relative that Einstein found intolerable. Bohr was not troubled by it. This is the part that is hardest to think about clearly. Not the physics, but the person, the fact of a human being who looks at the measurement problem, and the EPR argument, and the question of what happens to particle B when you measure particle A and does not feel the ground go soft. He felt something clearly because he thought about it constantly, but what he felt was not alarm. More like the deep engagement of someone in the presence of something genuinely profound that has not yet been fully articulated, and maybe cannot be, and maybe that is fine. He came back to the EPR paper repeatedly, wrote about it, talked about it at conferences, refined his response over years, produced language that became more precise without becoming more satisfying to the people who wanted a different kind of satisfaction. The language he settled into was something like, the EPR argument assumes that the properties of a system can be defined independently of the measurement arrangement, and this assumption is the thing quantum mechanics is asking us to abandon, and abandoning it does not create a contradiction. It only creates discomfort, and discomfort is not a physical argument. Einstein thought discomfort was evidence. He thought the feeling that something is wrong is sometimes, if you are careful enough, the earliest signal that something actually is wrong. He might have been right about that as a general principle. He was wrong about what was wrong here. But Bohr might also have been wrong, or at least incomplete, in a way that is harder to name. His answer was very good at explaining why you shouldn't expect quantum mechanics to tell you what the particle is doing when you're not looking. It was less good at explaining what the particle is doing when you're not looking. Whether that question has an answer is still, in a technical sense, unsettled. There are many interpretations of quantum mechanics, and they mostly agree on the predictions and disagree on the picture, and Bohr's Copenhagen interpretation remains one of the most widely cited and one of the least satisfying to people who want to know what is actually there. He died in 1962. His last blackboard, in his study at Carlsberg, had a drawing on it. The drawing was of the thought experiment from Einstein's 1905 paper on the photoelectric effect. He was still thinking about it. Still there, in the room, with the argument. The variable nobody could find. For 20 years after EPR, the theory kept working, and working and working, and the question of whether it was describing something real sat at the back of the room, like a guest who had arrived too early, and everyone was too polite to address directly. The accelerators ran. The calculations produced numbers. The numbers matched the experiments with a precision that made other theories look like rough sketches, and the community of physicists working on building things, reactors, lasers, transistors, the physical infrastructure of the second half of the 20th century, did not, in the main, spend much time on what the wave function meant when no one was measuring it. They used the theory performed, But underneath the using, something persisted. The something was the question of whether quantum mechanics was telling the full story. Einstein's version of this question, the version the EPR paper had planted, involved a specific hypothetical. What if there are variables the theory doesn't include? What if the particle does have a definite spin before measurement, and quantum mechanics simply hasn't found the mechanism that determines it? What if underneath the probabilistic surface of the theory there is a deeper layer, a deterministic layer, the layer Einstein had always believed must be there? This idea had a name, hidden variables. The name is almost too honest. The variables are hidden, not from the universe, but from the theory. They were there all along, encoding the outcomes, determining what the measurement would find. The theory just wasn't tracking them. The randomness of quantum mechanics, in this view, is not fundamental randomness. It is the randomness of incomplete information, the way a coin flip looks random to someone who cannot measure the force of the thumb. The hidden variable idea was not considered crazy. It was considered by most physicists probably wrong, and by many physicists not even wrong in the specific sense that it didn't make different predictions from quantum mechanics and therefore wasn't testable, and by almost all physicists not very interesting as a research direction, because even if the hidden variables existed, you couldn't find them. So what were you going to do with them? David Bohm, in 1952, actually did it. He constructed a hidden variable interpretation of quantum mechanics called pilot wave theory, or Bohmian mechanics, that reproduced every prediction of standard quantum mechanics exactly, and that described a universe where particles have definite positions at all times, guided by a wave that carries the quantum information. The theory was real. The theory worked. The theory required you to give up locality. The pilot wave was non-local in a specific technical sense, influencing particles instantaneously across distance, and this was, to most physicists, too high a price. Einstein read Bohm's paper and was not satisfied by it either, though for more specific reasons. The pilot wave was too artificial, too constructed, too much like a theory built to reproduce quantum mechanics, rather than a theory that had been found by following the physics. He continued to believe something simpler was underneath. He continued to not know what it was. The hidden variable programs continued in small pockets. Conferences were held. Papers were written. The majority of the field continued to not pay much attention, because the majority of the field was doing other things. Quantum field theory was being developed. Particle physics was accelerating. The universe was expanding in ways that needed measuring. The hidden variable question was a philosophical question in practical clothing, and the practical clothing did not fit well enough to draw a crowd. And here is the thing about a variable that stays hidden. It starts to do something to the people looking for it. Not immediately, gradually. The way any long search changes you, any search conducted in quiet without external confirmation, without the community approval that comes from working on a problem everyone agrees is worth solving. You start to wonder whether the variable is hidden because it is subtle, or hidden because it is not there. You start to wonder whether the act of looking is already a mistake. John Bell, working at CERN in the early 1960s, was one of the people who had not stopped wondering. He was a particle physicist by trade, working on accelerator physics during the day, thinking about the foundations of quantum mechanics in the hours that were technically his own time. He believed, or at least held open, carefully, the possibility that the hidden variables were real. He had read Bohm. He had read EPR. He had been thinking about what a hidden variable theory would have to look like to reproduce quantum mechanics, not in broad strokes, but in the fine details, in the specific correlations between entangled particles measured along different axes. And he found something. He found that the correlations were not free, that any hidden variable theory of a certain type, specifically any theory where the hidden variables are local, where the information encoded in each particle depends only on things in that particle's pass-like cone, would have to produce correlations that stayed below a specific limit, not as a choice, as a mathematical necessity, as a consequence of locality itself. The limit was not a guess, it was derivable. It sat there, in the math, and it was called an inequality, and it was called bells, and it said, if the world has local hidden variables, the correlations between entangled particles, averaged across many measurements and many angle settings, must satisfy this bound. And quantum mechanics predicted that the correlations would violate the bound. The chapter ends here, not because the story ends here, but because this is the moment the search for the hidden variable transformed from a philosophical position into something else entirely, something testable, something that the universe could be asked directly if you built the right instrument and asked the right question and ran the experiment long enough to trust the answer. The variable was still hidden, but for the first time there was a way to know if it was there. Bell's theorem without the theorem. He published it in a journal called Physics, not Physical Review, not Nature. A small journal, new, with a short run. The paper appeared in 1964 and was not immediately recognized as one of the most important things written in the 20th century. This happened sometimes. Bell was Irish, raised in Belfast. He had a particular quality. People who knew him describe it differently, but the common thread is something like, he took questions seriously that other people had decided to stop taking seriously, not contrarianism, something quieter, a constitutional inability to file things under settled when they weren't. The theorem he proved is not simple to explain without math, but its shape is simple. He asked, what must be true of any theory that reproduces the predictions of quantum mechanics if that theory is also local? Local meaning, what happens here is not instantly affected by what happens there. He was not asking this in the abstract. He was asking it in the specific context of entangled particles, where quantum mechanics says certain correlations exist that are in some sense too strong. Too strong for what? Too strong to be explained by anything determined in advance locally. Here is the shape of it. Imagine 3 settings for a measuring device, 3 angles, 3 directions along which you can measure the spin of a particle. Call them A, B, and C. You measure entangled pairs. Sometimes you measure both particles along A. Sometimes one along A and one along B. Sometimes B and C. Various combinations. You get statistics. You get correlations. You add the correlations up in a particular way and you get a number. Bell showed that if the particles carried local hidden variables, if their outcomes were predetermined locally, that number had a ceiling, a specific ceiling. The ceiling was not arbitrary. It followed from the assumption of locality with the same necessity that a proof follows from its axioms. You could not get above it if the world worked the way Einstein needed it to work. Quantum mechanics predicted a number above the ceiling, not slightly above, measurably, consistently, testably above. This means that if you run the experiment and get the quantum result, you have learned something about the structure of the universe. You have learned that local hidden variables are not it, that whatever is underneath, if there is an underneath, is either not local or not deterministic in the relevant sense, or both. The proof itself fit on a few pages. The implications filled decades. What Bell had done, without resolving the EPR debate, was transform it. Before 1964, the debate was philosophical. You could pick a side, Einstein's realism or Bohr's Copenhagen, and defend it with arguments and intuitions and the authority of your own thinking, and no experiment could settle it because no experiment had been designed to distinguish between them. After 1964, the debate was empirical, not immediately, not easily, but in principle and then in practice. You could ask the universe which side was right. Bell himself remained cautious. He did not say the theorem proved non-locality. He said it proved that you couldn't have both locality and the quantum predictions. One of them had to go. He had a personal preference, which was that locality might turn out to be the thing that goes, that the universe might genuinely be non-local in the Bell sense, not in a way that allows faster-than-light communication, but in a way that involves real correlations between distant events that are not mediated by any local mechanism. And he held this preference without certainty and without evangelism, which is the right way to hold a preference in physics. The experiments would come later. The theorem came first, and the theorem was enough to change what the question was. Not whether quantum mechanics was right. Everyone already believed it was right in the practical sense. Whether it was complete, whether the universe it described was the whole universe, or a projection of the whole universe, or a set of instructions for predicting what you would find in the universe without quite saying what the universe is. Bell's theorem said, now we can check, not the whole question, one corner of it, the corner that Einstein had been standing in since 1935, pointing. The theorem was 30 years old before it won Bell anything close to mainstream recognition. He died in 1990 of a cerebral hemorrhage, the day after learning he had been nominated for the Nobel Prize. He did not receive it. The space where an answer was going to arrive had been cleared. The answer, though, had not arrived yet. The experiments that didn't care about the argument. There is a type of scientific work that does not announce itself. It proceeds in laboratories that are not particularly large, run by people who publish in journals that the general public does not read. Funded through mechanisms that involve a great deal of paperwork, and the work itself consists mostly of building things that don't work, understanding why they don't work, making them work slightly better, running them overnight, checking the numbers in the morning, running them again. The drama, if there is any, is entirely internal to the people doing it. From the outside, it looks like maintenance. The Bell test experiments looked like this from the outside. From the inside, they were asking the universe a direct question. John Clauser was first, or close enough to first that the priority questions are more interesting to physicists than to anyone else. He was a postdoc in the early 1970s, deeply interested in the foundations of quantum mechanics at a time when this was considered, by many of his advisors an impractical research direction. He built an apparatus to measure the polarization correlations of photon pairs emitted from calcium atoms, and he ran the experiment, and the results violated the Bell inequality, and quantum mechanics was right, and local hidden variables could not explain the data. This should have been the end of the question. It was not the end because experiments have loopholes, not in the casual sense of ways to explain away an unwanted result, genuine technical loopholes, gaps in the experimental design that leave room for a local hidden variable theory to still, in principle, account for the result. The two most significant were the detection loophole, which arose because detectors in early experiments didn't catch every photon, leaving room for the possibility that the detected photons were an unrepresentative sample, and the locality loophole, which arose because in many early experiments the measurement settings were chosen before the photons left their source, leaving room for the possibility that the particles had known in advance what would be measured. Alain Aspect, working in Paris in the early 1980s, addressed the locality loophole. His experiment changed the measurement settings while the photons were in flight. Quickly enough, after the photons had separated, that no signal travelling at the speed of light could carry the setting information from one detector to the other. The particles couldn't have coordinated. The settings were chosen too late, and still the correlations violated the Bell inequality. Still, the quantum prediction held. The result felt like a door closing, gently, without drama, just the quiet click of a mechanism engaging. Then there was a long period of refinement, of closing loopholes one at a time, carefully, of building better detectors and faster switching mechanisms and more carefully shielded apparatus, and more rigorously randomized settings, and running longer experiments, and accumulating more data, and checking the statistics from more angles. The experiments ran. The inequality was violated. The quantum prediction held. Anton Zeilinger, over decades of work, contributed experiments of increasing precision and increasingly closed loopholes, and in 2015 a group in Delft ran what is called a loophole-free Bell test, an experiment that simultaneously addressed the detection and locality loopholes in a single run, and the result was the same. The inequality was violated. Local hidden variables are not consistent with what the universe does. The Nobel Prize in Physics in 2022 was awarded to Clauser, Aspect, and Zeilinger for this work. What they had proven, between them, across 50 years of experiments conducted at various temperatures and scales and distances, using photons and atoms and electrons and entangled pairs of many kinds, is this. The universe does not work the way Einstein needed it to work. The correlations between entangled particles are stronger than any locally predetermined arrangement can produce. Whatever is happening when you measure one particle and the other one instantly reflects that measurement, it is not because the answers were hidden in the particles all along. Something is actually happening. Not something that carries information faster than light. Not something that would allow you to send a message across any distance instantaneously, because the correlations only become visible when you compare measurements from both locations, and comparing them requires classical communication that cannot exceed the speed of light. The non-locality is real, but it is not useful in the science fiction sense. It does not grant access to anything. It only reveals a structure, the structure of a universe that is, in some precisely defined way, not separable into independent local parts. This is what the experiments proved. The proof accumulated quietly, over years, with instruments that broke and data that needed cleaning and graduate students who needed sleep. And the universe answered every time with the same number, violating the same inequality, holding the quantum prediction with a consistency that has, at this point, no credible alternative interpretation. What remains after the flaw is gone? The experiments are done, the numbers are in. The inequality is violated by every apparatus ever built to test it, across 50 years of attempts, across increasingly controlled conditions, and the conclusion has been recorded and published and peer-reviewed and awarded and cited until it has taken on the quality of settled fact. Local hidden variables are ruled out. The flaw Einstein needed is not there, and yet there is a specific feeling that comes after a long argument has been settled in a direction you did not want. It is not quite grief. It is not quite relief. It is something more like arriving at a room you have been walking toward for a very long time, opening the door and finding the room is different from what you imagined, differently shaped, differently lit, containing different furniture, and none of this is wrong exactly, but you need a moment to stop in the doorway and let your eyes adjust, because the map you had been carrying no longer quite describes the territory. Physics is in that doorway. The experiments say the world is not locally real, in the technical sense of these words. Local means effects do not propagate faster than light. Real means physical properties exist independently of measurement. The Bell tests say you cannot have both. One of them has to go. Most physicists at this point let go of locality, or rather, they accept that there is a specific kind of non-local correlation built into the structure of quantum states, while holding on to the no faster than light signaling rule as unviolated, because it is unviolated, and the two are compatible in ways that require careful language to explain. But saying locality is the thing that goes does not tell you what replaces it, does not tell you what the universe is actually doing when it produces correlations that no local mechanism can account for, does not explain what happens at the level of physical reality, not mathematical formalism, when you measure a particle in one location and its entangled partner 10 kilometers away instantly settles into the corresponding state. The math describes this. The math does not explain it. Explaining would require a picture, a story, a mechanism, something you could hold in your mind and say, yes, that is what is happening. The many worlds interpretation offers one picture. Both outcomes happen in branching versions of reality, and the correlation is preserved across branches because the entangled system branches together. The Copenhagen interpretation offers a different posture. Do not ask what is happening between measurements, because that question does not have an empirical referent. Bohmian mechanics offers a third. There is a real wave guiding real particles, and the wave is non-local, and that is simply what the world is. Relational quantum mechanics, cubism, consistent histories, each offers a different way of living with the same mathematics. Each takes a different piece of the problem as the piece you have to accept without further explanation. None of them is obviously wrong. None of them is obviously right. They all reproduce the same predictions. They are different stories about what the predictions are pointing at. This should maybe feel more settled than it does. The question has been narrowed enormously. The space of possible answers has been reduced. Local hidden variables are gone. What remains is a set of interpretations, all consistent with the data, all disagreeing about what the data describes, and no currently imaginable experiment to distinguish between them. The quantum world is determined in terms of what you will find when you look. What it is when you're not looking remains, in the precise technical sense, an open question. The floor is not there. What supports the building is something else, something that works perfectly, something that has never failed an experimental test, something whose predictions have been confirmed to absurd precision, something that underlies every piece of semiconductor technology and laser optic and medical imaging device built in the last 80 years. It works. We do not fully know what it is. Late at night, this sits differently than it does in daylight. The idea that the properties of things may not exist until someone checks them, that separated particles share correlations that no local story can account for, that the universe is in some sense less made of independent parts than it appears. This is easier to sit with when everything is quiet and the distinction between what exists and what you are aware of is already blurred by the hour. Or maybe that is just something I tell myself. The part Einstein got right. Inside the argument, past the EPR paper and the Bell theorem and the 50 years of experiments and the Nobel Prize and the settled conclusion that local hidden variables are ruled out. Inside all of that, there is a smaller thing that is rarely said clearly. Einstein was right that quantum mechanics was incomplete, not in the way he meant, not in the way that would have satisfied him, but in a way that turns out to be more interesting than what he was asking for, and more honest about the limits of what a physical theory can do, and more open toward whatever comes next. What he was right about is the interpretation problem. He was right that predicting correctly is not the same as explaining fully. He was right that a theory which tells you the statistics of outcomes without telling you what is actually happening is a theory with something missing. He was right to be unsatisfied with an answer that says, "Do not ask what is there when no one is looking, because that question is outside physics." He thought that was a refusal, not a resolution. He was not wrong about this. What he was wrong about was what was missing. He thought what was missing was a variable, some piece of information encoded in the particle, locally, that the theory hadn't found yet. He thought the gap was in the data, that there was more information in the system than quantum mechanics was tracking. The Bell test closed that door. The gap is not in the data. It is somewhere else. Where it is exactly is the question that remains. The interpretation problem, how to understand what quantum mechanics is saying about the nature of reality, not just the statistics of measurement, is a live problem in foundational physics. It is not considered as marginal as it once was. The work of Bell and Aspect and Zeilinger and everyone who followed them made it respectable again to ask what quantum mechanics means, not just how to use it. The question Einstein was asking, is this a complete description of reality, turns out to be a very good question. It just does not have a hidden variable answer. He spent his last years at the Institute for Advanced Study in Princeton, working on unified field theory, trying to find a framework that would combine general relativity and quantum mechanics into a single coherent structure. He did not find it. Nobody has found it. It remains the largest open problem in theoretical physics, the place where the two most successful theories in the history of science fail to agree, where the smooth curvature of space-time meets the discrete probabilistic machinery of the quantum, and the math breaks down. He worked on it in the morning. He went for walks. He played violin poorly and with great enthusiasm. He wrote letters. He argued in correspondence with Bohr and Born and others, with the same sustained conviction he had always had, never retreating from the position that the theory was unfinished, never making peace with the randomness at the bottom of things. His last written work was revisions to a scientific paper on his hospital bed 2 days before he died. He had asked for his glasses and his notes. What he left behind is not just the work, it is the posture, the refusal to accept "it works" as a sufficient answer to what does it mean, the insistence that physics is not just a calculator, but a description, that a theory which cannot say what is there when you're not looking has not fully done its job. This posture produced EPR, which produced Bell's theorem, which produced the experiments, which produced the most rigorous test of the structure of reality that physics has ever managed. And the result of that test is that the universe is stranger than Einstein's realism allowed for, and that is a result, and it is a real result, and it came from a man who was looking for something else entirely. The light was still on when he left the room, and what that means is that physics is still in there, still looking, still finding the room larger than the map suggested, still working by the light he left burning, which is the only kind of inheritance that compounds,